So welcome to the 46th Theoretical Physics Colloquium by Professor Ho-Ung from the University of Illinois at Chicago. He received his PhD from Yale University in 2003. Afterwards, he had several postdoctoral positions between 2003 and 2007 at the Korea Institute for Advanced Studies. Then between 2007 and 2010, he was a postdoc at the International Center for Theoretical Physics in Italy. Then he moved to Stony Brook, where he spent 2 years between 2010 and 2012. There, he received a Stony Brook Postdoctoral Achievement Award. In 2012, he received the faculty position at the University of Illinois at Chicago, and he was the Riken Biennial Fellow for the first 5 years there. He is a tenured professor since 2018 at the University of Illinois Chicago. He spent a year as a visiting professor at Kadanoff Center for Theoretical Physics in 2019-2020. His research interests include quantum chromodynamics, perturbative QCD, gauge theories via ADS-CFT correspondence, physics of heavy ion collisions, matter under extreme conditions, and even quasi-relativistic plasma of Dirac-While semimetals. And today he will be talking about spin, vortices, anomaly, and hydrodynamics. And with that, I'll give the microphone to Ho-Ung.
Thanks, Igor, for the very kind invitation and introduction. So I'm going to talk about the spin-related physics that summarizes some of my recent works. It looks somewhat sporadic and unorganized, but I fortunately found that my recent works can be collected in a single theme of spin physics. So let me just start out by saying that spin is one of the most quantum objects that capture the minds of physicists since early days of quantum mechanics. It has a discrete possible stage, which was clearly demonstrated in the experiment by Stern and Gerlach back in 1922. So now one of the fundamental property of massless, relativistic massless particle is that the spin is aligned with or anti-aligned with the momentum direction, which is called helicity. And under parity transformation, we all know that the angular momentum, such as spin, remain the same, where the momentum flips its sign. So from this, any correlation between spin and momentum breaks the parity symmetry. And this fact was the basis of the groundbreaking proposal by Li and Yang in 1956 and the subsequent experimental verification by Wu that the weak beta decay for nuclears can break parity symmetry. So in this example, the momentum of the emitted electron is anti-aligned with the original spin polarization of cobalt, which clearly demonstrate that the weak interaction breaks parity symmetry due to this anti-correlation between the spin and the momentum. Okay? Now, the same physics underlies the recent measurement of lambda baryon polarization in relativistic heavy ion collisions. In relativistic heavy ion collisions, this plasma can carry a large amount of orbital angular momentum, and some of this orbital angular momentum can be transferred to the spin polarization of the produced hadrons, such as lambda baryons shown here. And the lambda baryon weak decays to a proton and pion, as shown here. And the direction of proton is preferentially to the direction of the spin polarization of lambda, which is called this so by observing the direction, momentum direction of proton, we can get information about the spin polarization of lambda baryon. And this is possible precisely because the weak interaction breaks parity. So as is shown here in the differential decay rate as a function of the angle theta between the spin of lambda and the momentum direction of the proton, with the polarization coefficient alpha, which is non-zero, which signals the breaking of parity symmetry. And I'd like to also mention that although the parity is broken by weak interaction, the charge conjugation times parity, which is a CP, is still conserved by weak interaction, which means that this coefficient alpha should flip its sign when we consider the antivariant by charge conjugation transformation. Okay. So now, as another example of this introduction of the spins in high energy physics, I'd like to mention this proton spin puzzle, that the spin of proton which has to be given by the sum of contributions from quarks and gluons. And contrary to the expectation in the constituent quark model, where the proton spin arises solely from the spin of quarks, recent experiments seem to indicate that the gluon contribution to proton spin may be larger than the quark contribution to proton spin. And as a possible theoretical explanation, how this could be true, there may be some topological gluonic fluctuations inside proton that can flip the helicity of the chiral quark. I will talk more about these topological fluctuations related to chiral anomaly later. And by this process, on average, the quark spin contribution to proton may be small. But however, in this process, the angular momentum has to be conserved, which means that the difference in the quark spin has to be carried by the gluons in the form of some sort of back reactions. Okay. So now, probably one of the most fundamental consequences of helicity of massless particle is the chiral anomaly. So a Dirac particle, consider a massless Dirac particle. Dirac particle consists of, well, the Dirac fermion field consists of chiral wire fermions, left-handed and right-handed. And upon quantization, you get the particles and antiparticles with definite helicities. And this blue color indicate the negative helicities, and the orange color indicate the positive helicity. Under parity transformation, we flip helicity because helicity changes sign under parity, but it doesn't change particle to antiparticle. So the parity transformation acts horizontally in this table, whereas the charge conjugation changes particle to antiparticle, but without changing any helicity. Okay, so the charge conjugation acts diagonally in this table, and by definition, the axial charge is defined to be the net helicity charge, which is the sum of the blue color minus sum of the red color. And from this definition, we can see that axial charge is parity odd, but the charge conjugation even, because charge conjugation doesn't really change the helicity. Okay, and axial charge doesn't care whether it's particle or antiparticle. It only cares about the helicity of particle. So the axial charge is charge conjugation even, so that it is P odd and CP odd in summary. And there are not many quantities in nature that are P and CP odd. And one of them is this product of E dot electric field and magnetic field. And chiral anomaly states that in the presence of electric field and magnetic field parallel to each other, we can change the axial charge. Okay. And historically, this chiral anomaly was discovered by Adler, Bell, and Jacquet by computing this famous triangle diagram here, and it's sometimes called the triangle anomaly because of that reason. One of the important consequences of chiral anomaly in real-time transport property of plasma is the celebrated chiral magnetic effect. An easy way to understand how this could be possible is to note that in the presence of magnetic field, the spin magnetic moment of a massless particle aligns or anti-aligns with magnetic field to lower the spin magnetic moment interaction. And since spin is aligned with momentum direction, this induces a motion along the direction of magnetic field. And by working out which particle moves to which direction, we find that there is a current proportional to axial charge, which is parameterized by the axial chemical potential mu A here along the direction of magnetic field. So this is the celebrated chiral magnetic effect. And in equilibrium, there is a nice way of understanding why this chiral magnetic effect, the magnitude of chiral magnetic effect is related to the chiral anomaly due to the argument by Nielsen and Ninomiya. So let's consider the power. If we introduce some small additional electric field parallel to magnetic field, then power is given by E dot J. And then the same power should be equal to the change of the axial charge times the chemical potential of the axial charge. And by chiral anomaly, change of the axial charge is given by E dot B with this definite coefficient dictated by chiral anomaly. And by comparing these both sides, we conclude that the magnitude of chiral magnetic effect should be fixed by the magnitude of chiral anomaly with this specific coefficient here. Okay. Now, on a more experimental side, a golden opportunity of observing this chiral magnetic effect in experiment is the isobaric collisions in RIC between the rubidium, comparing the collisions of rubidium and zirconiums. So by colliding this charged heavy ions, we create a huge strength of magnetic field due to the relativistic velocity of these heavy ions. And due to the chiral magnetic effect, there may arise charge separation along the direction of magnetic field. And since the rubidium and zirconium has different charges, their magnetic field produced can be as large as 20% different, and so the amount of charge separation can be different, which can be or might be observed in some of the correlation functions of charged pions produced in the experiment, and we look really forward to an interesting outcome from this experiment in the near future, which at the moment is in the status of data analysis. And now I mentioned that the amount of the chiral magnetic effect is fixed by chiral anomaly, but that is true only in the equilibrium. And if we consider the out of equilibrium considerations, such as the time-dependent magnetic field with frequency omega, then the amount of chiral magnetic effect can depend on this this frequency omega in a very non-trivial way. So here in the plot, we show the computations in both perturbative QCD, represented by these solid lines, and those from ADS-CFT correspondence, represented by the dashed line here. Blue color means the real part, the red color means the imaginary part of this response function, chiral-magnetic effect response function, sigma omega. And for example, the slope of the imaginary part at zero frequency, denoted by zeta 5, can have a very non-trivial dependence on the nature of the interactions. And as an example, if you compute this quantity in perturbative QCD in leading log approximation, you see that its dependence is very similar to how the other disruptive coefficient like shear viscosity and charge conductivity depend on the coupling constant. Okay, so this plot clearly indicates that the chiral magnetic effect away from equilibrium at finite frequency is not just dictated by anomaly. It depends on a lot of more interesting dynamical aspects of the interactions. And by careful study of such dynamical aspect of chiral magnetic effect in decoupling picture, we find that there are roughly 3 different contributions at finite frequency. So the first contribution, which is called the equilibrium contribution, arises from the spin alignment along the direction of magnetic field in equilibrium distribution function to minimize the spin magnetic moment interaction energy with magnetic field. And since it relies on the equilibrium, it exists in small frequency regime, but it is lost in high frequency far off equilibrium situation. And the second contribution, which is more kinematic, comes from a topological nature of the chiral spinner of wire fermions, something called the Berry connection in the momentum space. And since its nature is topological, it doesn't really depend on whether it is small frequency or high frequency, so it stays the same. And the final contribution, which is called the magnetization current, is illustrated in this figure. So suppose that we have a time-dependent magnetic field. Then due to Faraday effect, there is an induced electric field in the circular direction. And electric field accelerates the charged particle, so the momentum changes. And due to helicity relating momentum and spin, this induces the change of the spin polarization of the plasma. And in the presence of G factor relating spin to magnetic moment, we eventually get the increase of or change of the magnetic moment in the plasma. And by computing the magnetization current, which is curl of the magnetic moment, we find that this magnetization current is along the same direction of the original magnetic field. And from this illustration, it is clear that this effect exists only in finite frequency or time-dependent magnetic field case. So that's why this magnetization current contribution exists only in finite frequency, whereas it is absent in equilibrium. And so this is a nice budget table of the chiral magnetic effect in both in equilibrium situation and the off equilibrium situation, depending on the amount of frequency related to the relaxation time of the system. Okay. Now, one of the consequences of chiral magnetic effect is in hydrodynamic regime is the existence of collective propagation of chiral charges, which is called the chiral magnetic wave. And it is very easy to understand how this phenomena comes about since the current is proportional to magnetic field times the charge density. By plugging that into the conservation equation of charge, we get a wave equation with unidirectional propagation velocity v chi, depending on the chirality of the charge. So the left-handed charge moves to a particular direction along the magnetic field, whereas the right-handed charge moves to the opposite direction, and there is a charge separation due to this chiral-magnetic wave, which may induce some quadruple moment of the charge distribution in the fireball created in relativistic heavy ion collisions, which may have some distinct signals in the charge-dependent elliptic flow of pions, which I will not discuss in detail. So with all this introduction to the chiral anomaly, let me now finally mention that this anomalous transport phenomena exists not only in the current proportional to magnetic field, it also exists in the current proportional to vorticity of the fluid, omega here, which is called the chiral vortical effect. And also it exists in the momentum or the energy flow of the system in the presence of magnetic field and vorticity. You may call this the kind of analog of chiral magnetic effect for the energy flow instead of charge flow current. But some of them are related. For example, the chiral vortical effect and this coefficient for the momentum current, proportional to magnetic field, is related by time reversal symmetry, which is very similar to Onsager's relations, and it is also possible to show that their equivalence persists even in finite frequency and momentum. Yeah, so that's. Now, I'd like to go into a somewhat deeper understanding of chiral anomaly, and this old picture of Gribov seems quite intriguing. So, so let's consider, say, one Y fermion, say right-handed, put in a magnetic field, background magnetic field. Then we all know that the transverse dynamics is frozen into the discrete Landau levels, whose two-dimensional density of state is proportional to magnetic field here, whereas the motion along the direction of magnetic field is still free. And here on the right, we plot the energy spectrum as a function of the momentum along the direction of magnetic field. So we have Landau levels here. But what is important, what is essential is not the shape of the, not a detailed shape of the spectrum. What is important is that the chirality of the Y fermion manifests itself into the existence of something called zero mode, shown as this line spectrum here, a linear spectrum, with a level crossing at zero energy. Okay, and why this is related to chiral anomaly is the following. In the vacuum, we all know that the Dirac sea, all the states with negative energy are filled up to energy zero. And if we now apply the additional electric field along the direction of magnetic field, then these particles are accelerated, meaning that their momentum grows linearly in time proportional to electric field. So there is a spectral flow in time where the field C, the Fermi level goes up from 0 to finite amount. So you can see that this additional part can be thought of as a created new particles out of vacuum by applying the additional electric field. And we know that the transverse density of state Landau level is given by magnetic field, and the one-dimensional density of state is 1/2 pi dp z, And by working out this, we see that the three-dimensional axial density changes in time, changes time in which agrees precisely with the chiral anomaly with the right coefficient here. I like to mention that in this picture, what is counted is the particle number, the fermion number, which is clearly gauge invariant. So therefore, this produces the covariant gauge invariant covariant anomaly with correct coefficient here. It doesn't explain the consistent anomaly in this picture. So that's the comment. So now, recently in condensed matter systems, there appeared many interesting spectrum of quasi-electrons, and by engineering some of these spectrums, so we can get a sort of analog of massless particles in high energy. But the dispersion relation or the Hamiltonian, Dirac Hamiltonian, can be much more complicated. For example, here we showed that well, in this example, it is what is shown here is the Hamiltonian, where the coefficient in front of Dirac matrices or the Pauli matrices are the some polynomials in momentum k with power n. And if you put this quasi particles in magnetic field, just like what we did, then you get the same sort of Landau levels in transverse space. But then but the energy spectrum along the longitudinal direction looks quite interesting here. So instead of having just a single zero mode, so crossing single zero mode with level crossing, we get the n number of such level crossing zero modes. And by the argument of the Gribov applied to this case, we see that the chiral anomaly is enhanced by this number of level crossing zero mode, which is this degree of polynomial n here. So this leads us to a question whether we can say something about the chiral anomaly in a more general situation of having an arbitrary coefficient function in front of Dirac matrices in momentum, denoted by this p vector as a function of momentum k. Now, the problem of computing anomaly in this case becomes a somewhat complicated mathematical problem. In both the heat corner method, which is essentially the Fujikawa's method, and also in an explicit diagrammatic computation of triangle anomaly, we showed that the chiral anomaly in this general situation is proportional to the winding number of the map between the momentum k to this coefficient function p in infinitely large radius of in the infinite radius sphere in momentum space k. So this quantity just measures how many this map wraps around the two-dimensional sphere at infinite radius of k, which can be called the winding number. But instead of line, we are talking about really two-dimensional sphere wrapping around multiple times. And the chiral anomaly is precisely proportional to that winding number of the map from the momentum k to this coefficient function p here. Now, the implication of this is quite interesting, because it can be also shown that the winding number of this map is equal to the monopole charge of the Berry curvature of the chiral spinors with this Hamiltonian here. So by chiral spinor, we mean the eigenstate of p dot sigma with eigenvalue, say, plus p here. And now, instead of p, we now have p as a function of k. And from this, by using the chain rule, it is easy to see that the Berry connection in k space is given by the pullback of the Berry connection in p space by this pullback matrix, which is precisely the derivative of k respect to k. And the corresponding Berry curvature is also given by the pullback of the Berry curvature in the p space to k space by this pullback matrix. And it is easy to now see that the monopole number in k space is equal to the monopole number in p space, which is a unity, times how many times this map from k to p wraps around the two-dimensional sphere where we compute the this monopole charge. So therefore, this winding number is precisely equal to the monopole charge of the Berry connection in the momentum space of k at large radius. And this Berry monopole is precisely appearing in the kinetic theory of chiral fermions called the chiral kinetic theory. And so that means that there is a rigorous connection between anomaly that is happening at the zero momentum region in infrared and the high momentum region described by the chiral kinetic theory. So I like to emphasize that this is a manifestation of one of the fundamental characteristics of the anomaly, which is the UV-IR connection. So this index theorem, which is the Euclidean version of the chiral anomaly, on the left-hand side, we have an index of Dirac operator as a difference of the zero modes with plus chirality and minus chirality. And by definition, this index is infrared quantity by definition. Now the non-trivial theorem by Atiyah and Singer is that this infrared quantity can be expressed in terms of something, some topological density locally defined in space, which is the which is ultraviolet quantity. So this index theorem is a manifestation of the ultraviolet infrared connection, and I like to emphasize that what we have discussed is another manifestation of this UV-IR connection. So by definition, anomaly happens at the zero momentum region, the level crossing point. So by definition, it is infrared quantity. Now, by rigorous mathematical computation, we found the connection of that to something defined in UV, which is in large momentum region, given by the Berry monopole charge of the chiral spinors. So this is a manifestation of the same UV-IR connection now in momentum space. Okay. Now I'm going to talk about now something different, which is the spin of magnetic vortices. So as we know well, in the superfluid phase, the bosons, the macroscopic number of bosons occupy a single quantum state, and in the case of having a vortice, superfluid vortice, the n number of bosons occupy a single quantum state carrying a unit of the angular momentum h bar, so that the angular momentum of the vortex is given by just h bar times number of particles, number of bosons in the system. However, if we consider the magnetic vortices, threading a magnetic flux at the center, then the canonical momentum given by P is still quantized to be an integer, but due to the presence of vector potential induced by the magnetic flux, the gauge invariant momentum is no longer quantized, and correspondingly, the angular momentum computed with this gauge invariant momentum is not just multiple of h bar, and this non-integer nature of angular momentum is a special feature that is only possible in 2 dimensions, because the representation of the rotation group in 2 dimensions can have any quantum number. So now here comes a sort of thought experiment asking the angular momentum conservation. So suppose we start from some initial condition without any magnetic vortex, and then we turn on the magnetic flux by this external solenoid to create sort of sort of the situation we have here for. Then we see that the gauge invariant angular momentum of the metal part is not 0 because of this presence of magnetic flux. But however, we can turn on this magnetic flux in a completely rotationally symmetric way, so that we must have an angular momentum conservation in the total system. So where is the compensating momentum? And this is a typical example of the Feynman's angular momentum paradox. And the resolution of this paradox is the following. So the magnetic flux produced by this solenoid has to come back somewhere outside of the solenoid, because the divergence of magnetic field is 0. And at the same time, the very fact that the particle we are considering is charged means that by the Gauss law, there must be a radially pointing a electric field in the system. And from this electric and magnetic field, there is a pointing vector along the tangential direction in this figure. That means that there is a finite amount of angular momentum carried by the electromagnetic field, given by this. And after careful integration of this angular momentum of electromagnetic field, one can show that it precisely matches with the metal part of angular momentum, so that the total angular momentum is indeed 0. So this example illustrates the fact that by turning on the magnetic field to create the magnetic vortex, the total angular momentum has to be 0 because of the angular momentum conservation. And that fact can be easily seen in the example of relativistic magnetic vortices. And in the case of neutral Nielsen-Olesen vortex, which clearly doesn't have any angular momentum because it doesn't have any momentum. And that fact can be understood simply by that in that case, the neutral Nielsen-Olesen vortex can be thought of as a combination of the particle vortex and anti-particle anti-vortex, whose angular moment and their angular momenta cancel with each other to give rise to a 0 total angular momentum. And here is the reason for this this argument. The phi, which carries the winding number in angular direction phi, is a sum of the particle operator A and the complex conjugate of anti-particle operator B, so that the particle and anti-particle carry a opposite vortex number, winding number, so that their angular momentum in the neutral case cancel with each other. And this aspect of zero angular momentum for relativistic magnetic vortices can be also seen clearly in the in, in the recent discovery of a particle vortex duality in 2+1 dimension, where on one side you have a abelian Higgs model with dynamical electromagnetic field. In that case, in the symmetry breaking phase, you have a magnetic vortex. Now, in the dual description, we simply have a complex scalar particle without any dynamic electromagnetic field. And under this duality map, the magnetic vortex maps to elementary excitation of scalar particle on the other side. And it is clear that the magnetic vortex should not have any angular momentum in order for this map to be consistent with each other. Now, this argument becomes more subtle when we consider charged Nielsen-Olesen vortex, where the contribution between particle and antivortex no longer cancel precisely. In that case, if you work out carefully the electromagnetic contributions, then you can still show that the total angular momentum is zero, consistent with the angular momentum conservation here. And as another non-trivial example, we can consider this interesting non-abelian vortex in color flavor locking phase. So essentially, this vortex is a combination of the fractional superfluid vortex and the color magnetic vortex, which can be seen here. There is a global U1 baryon number superfluid winding number in front, and there is a color magnetic vortex phase here. And in this example, by carefully computing the matter contribution and the color gauge field contribution to the angular momentum, it can be shown that the total angular momentum doesn't get any contributions from the dynamical color gauge field, so that it is solely given by the superfluid vortex part, global superfluid vortex part, NB. So this nicely illustrates kind of the absence of the angular momentum in the magnetic vortex in a more non-trivial setup here. And I just like to mention that this angular momentum nicely matches to what you would find in the hadronic phase in terms of dibaryon or superfluid condensate. Okay. Now, as a last example, the situation in the case of topological insulator, in this example, the situation is somewhat different. So here we are considering say the boundary of topological insulator, and we know that the on that two-dimensional boundary of topological insulator, we have a quantum Hall effect of level 1/2 given by this. So in the presence of some magnetic flux onto that surface, there is an induced charge, and in the presence of electric field, we have some quantum Hall current given by this expression. And let's imagine turning on the magnetic field initially from 0 to some finite amount. Then as magnetic field increases, there is a charge appearing due to this relation here. And at the same time, by Faraday's effect, we get electric field in tangential direction. And by the quantum Hall effect, there is an induced current along the direction, along the radial direction here. And as a consequence of the Lorentz force, we have a, so then the Lorentz force, the sense that there is a force induced by the radial current and the magnetic field, And just by using these relations, we can show that the net force turns out to be 0. So that in this time-dependent process of turning on magnetic field, there's no torque acting on the matter part, so that so that means that the matter contribution to angular momentum here should be 0. So then the only angular momentum for this system can be from the electromagnetic part. Again, here because there is an induced charge here, there is a electric field produced by that, by the Gauss law. And from the magnetic flux and the electric field, we can have a non-zero contribution of electromagnetic field to the total angular momentum. And by evaluating that contribution, we get something fractional angular momentum in unit of h bar. Now, so the question is, what happens about the angular momentum conservation in this process? So what happens is that the incoming magnetic flux localized in one region has to come out in other parts in the topological boundary, and in that other part where magnetic flux leaves the topological insulator, there is precisely opposite angular momentum sitting in the electromagnetic field, so that we can think of this as a consequence of transferring fractional angular momentum from one boundary to the other, and that satisfies the total angular momentum conservation globally. But locally, we could have some fractional angular momentum localized around the magnetic flux here. Okay.
Sorry, can I ask a question?
Oh yes, please.
Is it that quantity related with the whole viscosity of the system? Because in principle, the whole viscosity of this type of topological phases are related with the angular momentum per particle of the.
Yeah, I think that's a very good question, but I have to admit that I don't know much about whole viscosity. But it seems to be a very interesting question to think about. Yeah.
Okay, thanks.
Okay.
Yeah. Any other questions before? Yeah.
There were no raised hands so far.
Okay. Good. So now let's talk about this macroscopic manifestation of spin degrees of freedom in the hydrodynamic description. So I'm going to talk about the spin hydrodynamics that has been recently discussed a lot in the community, and the associated notion of pseudo gauge transmission. What is the physics meaning of pseudo gauge transmission in the spin hydrodynamics? So let me motivate the idea of spin hydrodynamics by considering this cylindrical geometry, which is one of the possible global equilibrium with total angular momentum conservation if there's no friction in the wall. And so the equilibrium is not only specified by the total energy and total particle number. In addition, there is a total angular momentum in the system characterizing the equilibrium configuration. And now by equilibrium, we mean that the entropy is extremized. So let's suppose we consider some arbitrary process of exchanging energies and particle numbers and the angular momentum between two regions, 1 and 2. And since the entropy has to be extremized under such exchange of the conserved quantum numbers, its differential has to be given by this form with the Lagrange multipliers in front of change in energy and change in particle number. Now, in addition to that, we should also have have a Lagrange multiplier corresponding to total angular momentum conservation here. And that is a vector-like quantity, which may be called the potential corresponding to angular momentum. It will be eventually called spin potential that I will explain shortly. So now this total angular momentum in the presence of spin is the sum of the orbital angular momentum x cross p and the spin. And after plugging this expression into that entropy relation, first law of thermodynamics, and rearranging terms, we end up to this expression, okay, where this omega not only sits in front of the spin now, it also sits in front in the fluid velocity part, which is conjugate to the momentum conservation here. Okay. Now this means that the this omega appears as a fluid velocity in the system, and that same constant fluid velocity appears in front of the differential of the spin density in the system. So the fact that the same omega appears in both spin spin density differential part and the momentum differential part means that there is a non-trivial so that part is a reflection of the fact that only the total angular momentum is conserved, not individual either orbital or spin. Okay, so so this indicates the necessity of modifying the first law of thermodynamics in the presence of spin density, and which closely related to the vorticity. So essentially, the Lagrange multiplier for the spin density is provided by the fluid vorticity, which is a reflection of the fact that the orbital angular momentum, orbital angular momentum and spin angular momentum can be exchanged. In the system. All right. So then this aspect can also be seen in this way. So this is the expression of the total angular momentum tensor, which is sum of the orbital angular momentum part and the spin angular momentum part. Now, if we impose the conservation of total angular momentum, we obtain the relation between anti-symmetric part of the energy momentum tensor and the change of the spin density in time here. So this relation is a reflection of the fact that the angular momenta can be exchanged between orbital and spin part. So the left hand side is basically a torque acting on the orbital part, whereas the right hand side is change of the spin. And in this description, we see that in the presence of spin tensor, the energy momentum tensor cannot be symmetric anymore. It has to contain the anti-symmetric part. And this energy momentum tensor is called the canonical energy tensor, which can also be seen in a more microscopic definition of energy momentum tensor from the Noether method. But I won't go into that detail. So the only point in this discussion is that presence of spin dictates that the energy momentum tensor should contain anti-symmetric part in the description. Now, based on this, we can develop the spin hydrodynamics by considering a local equilibrium, which is a slowly varying deviation from the global equilibrium. So there is a symmetric part, the usual symmetric part in hydrodynamics. In addition, we need to add this anti-symmetric part. And by working out the second law of thermodynamics with modified first law of thermodynamics that I showed before here, we can find that there is a non-zero energy flow perpendicular to the boost spin direction and the gradient of temperature, which is precisely the definition of the Sommer-Hall effect. Now I like to emphasize that in this limit, the entropy production is 0. So we have an ideal limit of spin hydrodynamics. And in that limit, we can have a sum or Hall effect. And this is one possible terms in spin hydrodynamics. For a more complete list of terms, please refer to the other very interesting paper by these colleagues. Okay. Now, now I'm going to talk about pseudo gauge transformation. So it has been known that the by this strange looking transformation of energy momentum tensor and the spin tensor, the conservation of energy momentum is not modified. So the
Ho-Ung?
Yes, please.
There is a question. Masood
yes,
Chokri, go ahead.
Hi, I wanted to ask a question about the previous slide.
Yes, please.
In this d mu s mu, you got something minus beta mu plus d mu beta. Isn't this term equal to 0 in equilibrium?
Yes, yes, yes. Yeah, you are absolutely correct. So I'm afraid I don't have much time to go into that detail, but so you are absolutely correct. So this is trivially 0 by using equations motion. Now what we can do is to introduce impurity in the system, modifying the equations motion. And by putting impurity, we can show that we can define something called no Dirac frame, which is the frame which the static impurity doesn't experience any Dirac force. So that's the definition of no Dirac frame. And so in that case, this quantity is given by the force acting on the impurity. So it's no longer 0. And by putting this condition, that is this being 0, is equivalent to saying that we are choosing our frame to be a no Dirac frame.
Mm-hmm.
I know that this explanation is probably not understandable in simple, in the simple words, but there is a way of having this non-zero by putting impurity to justify this conclusion in the no Dirac frame.
Thank you.
Okay. Yeah.
Excuse me.
Yes, please.
Yeah, just this is an immediate follow-up. Is this I mean, when you're choosing you choose a frame here, if
Yes.
you perturb a little bit, you will have like spin waves and density waves separately? And in this case, in what sense is your entropy maximized? And also, will it be causal equations of motion? I mean, you quote Enrico Speranza and co-authors, but they also show that the collision term is non-local. I mean, this is about your next slide.
Yeah.
So I'm not sure in what sense is this defined. I mean, you call it ideal and the entropy current is 0, but the linearization, the causality is dubious, and you don't have, you don't just have a sound wave and a vortex if you want, or a mixture. You will have spin waves and stuff like that.
Yeah. I think so can we think? I think probably you're talking about these collision terms, which induce some dissipative terms in addition to this ideal limit, right?
Yes, but it's also non-local. It cannot go to 0 locally.
Yes. I think we are doing gradient expansion here. So that non-locality in collision term will appear as a gradient corrections in hydrodynamic regime, I think.
But then it will be causal. Then it breaks causality.
Causal, yeah. So I understand that basically you are saying that this ideal limit may not be causal by itself. Yes. So I think the best way of looking at this is to consider this as just a leading term in the gradient expansion, And for more complete, well-defined causal theory, we probably need higher order distributive terms to ensure the nice property of theory. But this term will appear as a first leading order term in that this derivative expansion. I'm not sure I answered your question satisfactory way.
Okay, thanks. I mean, we'll discuss later. Thanks. I don't want to.
Okay.
Yeah, let's keep the longer discussions for the end.
Yes. Yeah. So I think I'm almost to the end. Hopefully. So now, so there is such a pseudo gauge transmission which looks like some redundancy in the hydro description of the theory. And I like to mention that the physics meaning of this pseudo gauge transmission is very similar to what we already know in electrodynamics. Then the system with magnetization can be equivalently described in view of the external gauge field by the magnetization current. So the external gauge field cannot distinguish between the magnetization and the magnetization current. And similarly, the Einstein gravity cannot distinguish with this cannot distinguish between the spin polarization and something called the spinitization momentum, which I coined, which is precise analog of magnetization current for magnetization density. So so the meaning of pseudo gauge transformation is the inability of hydrodynamics to distinguish between spin density and the corresponding spinitization momentum without any spin density at all. And by this pseudo gauge transformation, starting from ideal this ideal spin hydrodynamics, after doing pseudo gauge transformation, we end up to having several non-dissipative second-order transport coefficients related to vorticity. It's non-dissipative because the pseudo gauge transformation doesn't change the conservation law. So the second-order transport coefficients do not produce entropy. In that sense, it's still ideal, but in terms of gradient expansion, it is a second order, which is quite interesting by themselves. And it's also possible to derive this second order non-dissipative transport coefficient starting from conventional hydrodynamics by imposing the this ideal this non-creation of entropy in the system. And so now the more important question is, why do we have these equivalent descriptions? So in fact, there are infinitely many pseudo gauge transformation with continuous parameter t in this case pseudo gauge parameter sigma, and the hydrodynamics really cannot distinguish between these infinitely many equivalent descriptions. And one way of understanding is the following. So given a microscope theory containing, say, several constituents, microscopic constituents carrying spins, one could choose, say, canonical energy momentum tensor for one constituent, or you can choose a symmetric energy momentum tensor by doing the pseudo gauge transformation for other constituents. And that's just your choice of describing your system in macroscopic regime. And the hydrodynamics cannot really distinguish your choice that you have made in your description. So that all these discrete choices are equivalent in some sense in hydrodynamics. There's a one-to-one map we can establish between the two different descriptions. However, the main point is that hydrodynamics is a universal theory. It has to be, it should be applicable to any situation, independent of what microscopic theory you have. So that means that the only way the hydrodynamics can be consistent with this possibility of choice is that it should allow a more generous equivalences in its description with continuous parameters in order to accommodate any microscopic situation you might have. So this is a consequence of kind of invisibility of hydrodynamics, invisibility in hydrodynamics of these microscopic details of the system. But hydrodynamics has to cope with that microscopic detail. So that's kind of a conceptual explanation why there exists such a pseudo gauge transformation with continuous pseudo gauge parameters. So I think I should end at this point, and thank you very much for your attention.
Okay, thank you. Thank you so much for the presentation. Now we will have some time for questions, and I think Giorgio wants to start.
Yes, please.
Sorry. Yeah, regarding your last point about the pseudo gaugization, which I think is sort of the heart of the matter. Your entropy current, I mean, is conserved, although maybe there are problems with causality, as you said, but is the entropy pseudo gauge dependent or not?
Oh, that's a good question. In fact, entropy density depends on pseudo gauge transformation. Yeah.
I mean, pseudo gauge, just sort of as a follow-up, you can derive pseudo gauge transformations. They have a meaning in the microscopic theory as a field redefinition together with a coordinate redefinition. They are a generalization of angular momentum. Entropy is the number of microstates. It's the law. It's the log of the number of microstates. I mean, I find it really worrying that entropy depends on the pseudo gauge.
Yeah, that's a fair question, and I think I have an answer to that question. What we are modifying is the entropy current by this total divergence term. So the total entropy obtained by integrating that entropy density current over the hypersurface remains the same. So what we are doing is just locally relocating the entropies from one point to the other, and that freedom seems to be inherent in the description because of maybe some of this non-local nature of the this spin effect, like this.
I mean, just as a sort of, if you had a gauge theory, for example, where you had, color domains or something like that, but you also have local equilibration. Pseudo gauges are generally also correspond to gauge transformations in the sense that if you change the gauge, you also change the pseudo gauge. In this case, you're shifting the entropy by a gauge dependent quantity, right?
I think I have the same answer. So we are not really changing the total entropy, which is the integral of entropy current over hypersurface. That remains the same under this transformation, because this is just total divergence term.
What we are doing, derivative. Yeah.
Yes, it's total. The conservation is not modified. So what we are doing is sort of exploiting some of the non-local ambiguity of how we distribute this entropy in space.
Okay.
Well, that seems to be somewhat ambiguous here.
Is that all? I don't want to interrupt, but if that's...
Please continue. Yeah. Maybe if there is time, I'll ask for it.
Okay. Next question, Kenji Fukushima.
Yeah.
Yes. So thank you very much for a very nice talk. Wonderful. And so please go to the slide, maybe 2 pages before the end.
Oh.
I saw that well,
here.
So the canonical for maybe not this one, but yes, this one, yes. The canonical, yes. The canonical energy momentum tensor for some degrees of freedom and very infante for other degrees of freedom. So I want to know what is the criterion to choose whether it should be canonical or very infante. So some and other, what do you mean precisely by some and other?
My answer is that there's no meaning.
What?
That it is just a choice to make. So given microscope theory, suppose you have, say, U quark and T quarks. And it seems to be a matter of choice how you describe the spin degrees of freedom for U quark and T quark. So for U quark, you may choose canonical description, whereas for D quark, you could choose Bellefontaine or the other, or you may choose Booth canonical or Booth Bellefontaine. So they all give you a different looking hydrodynamics, but there is a one-to-one map between different description, so that they are the equivalent description of the same theory, right? And that freedom of choice manifests itself.
Okay, so then probably it is you. It is then, if I understand correctly, then it is you who choose a theory or microscopic hydrodynamics, and then once you make such a choice, then it makes a choice of the some degrees of freedom, or the
Yes.
the canonical and Bellefontaine.
Yes, yeah, that seems the choice, and there are various choices.
Yes, probably. My concern is somehow related to the previous question by Jojo, and but so if you consider the gauge theory, for example, then the canonical is not really a gauge invariant, and so how do you deal with the gauge invariance? Not pseudo gauge, but the gauge invariance.
I think you are considering the gauge theory.
Yes.
Yeah,
So
I think
it's
that's
probably
more
really hydrodynamics. So maybe as long as you consider the hydrodynamics, it is probably fine. But if you see the microscopic structure of the energy momentum tensor, then the gauge theory may have some problem, right? The canonical is not really a gauge invariant. So probably usually the people say that the Bellefontaine is gauge invariant. It is preferable choice.
I see. So I understand that that's quite interesting. That so a priori the gauge invariance is a different question than this question of this two different choices of energy momentum tensor, right?
Yeah.
But now you are saying that the Bellefontaine choice is preferred.
Yes.
Because of the gauge invariance in the case of gauge theory. I think that's very interesting. Yeah, I haven't thought about that, and yeah, thanks for letting me know that.
Okay. Thank you.
Okay. Next question is Fran Peña Benitez.
Yes. Hi again. Yes, I have a question. I mean, I don't know if I'm confused with the discussion with of the spin hydrodynamics. So the point is that hydrodynamics in the end is about transport, right? So and then you made like, can you go like a few slides back where you were doing this analogy between magnetization and that's spinetization or whatever. So if we are talking about transport, magnetization currents are not, you can, by a transport experiment, you cannot measure a magnetization current. So then
that's correct. Yeah, I think so.
Then the point is that if we want to include spin into hydrodynamics, but you are concluding that it's just like an analog of magnetization, by a hydrodynamic experiment, you will never be able to measure spin transport because it's not real, transport. Am I like missing something?
No, I think I agree with you. Yeah, within hydrodynamics itself, there's no way to distinguish these different descriptions. So in that sense, hydrodynamics, that's a inevitable inability of hydrodynamics as a macroscopic universal theory. It cannot really probe the microscopic details in macroscopic scale.
Okay, so then from your current view, does it make sense to try to introduce spin degrees of freedom in hydrodynamics?
Yes, it makes sense. The only point we are trying to make is that whether you introduce spin or not in hydrodynamic description is a matter of choice. And there is a one-to-one correspondence between two descriptions. So in that sense, they are completely equivalent. So in other words, a given solution in one description you can obtain uniquely the solution in the other description. There's a one-to-one map. That's what pseudo-gauge transformation tells us. So so then conceptually, the only question is why do we have such a freedom of descriptions? And we seem to and our yeah. So what we are trying to say is that this is because of the macroscopic nature of hydrodynamics that is not able to probe the microscopic detail.
Okay.
Okay, let's move
Thank
to
you.
the next question. Giorgio again, go ahead.
Yeah, no,
Yes.
this is a follow-up actually.
Yes,
That
yes,
I'm
yes.
actually, I mean, this I find it a bit difficult to accept because from the point of view of statistical mechanics, the division of angular momentum into spin and vortex type angular momentum is very well defined. You count microstates, spin has a bunch of microstates, momentum, it's an equilibrium. You can measure it on the lattice, and it has been measured on the lattice by Hirono et al., the spin susceptibility. So I do not understand in what sense, if it's measurable in global equilibrium, you should be able to discretize many global equilibriums and get a hydrodynamics out of it, which is both detectable and well-defined. It's not just a matter of convention, how much spin gets absorbed into microstates and how much spin causes motion. You see,
You are absolutely correct. Yeah,
I think,
you are absolutely correct. This is
please go ahead. Yeah.
So so let me clarify again. Our claim is not that spin is unphysical or something that that can be just removed. What we are saying is that the operators that is described by hydrodynamics is the operator that couples to external gauge field and external metric. So those are the only operators that hydrodynamics deal with. And for those operators, specific choice of operators, there's no difference between magnetization and magnetization current. Of course, you can probe your system with a more refined set of operators, like real maybe spin polarization of lambda baryons by observing proton directions. So those are more refined operators. But hydrodynamics, in this sense of definition, do not really describe such refined operators.
Can I just do a quick follow-up, because I think there is a very important point. It depends a little bit on how do you define hydrodynamics. If you define hydrodynamics in an Eulerian sense, so in terms of conservation laws, I think this is what's going to happen here. Yes. But if you define hydrodynamics as Lagrangian hydrodynamics, not necessarily with a meaning Lagrangian, but meaning you track a particle, you track a volume element, and you see what happens to it, the Lagrangian picture. Then what you are saying, I don't think it's true. You can define a Lagrangian picture of what happens to a particle, which is dependent on the pseudo gauge, which is dependent on the pseudo gauge, and which distinguishes between what is a spin density and what is an angular momentum density. Simply, conservation laws do not give you the full dynamics. Conservation laws do not give you the full dynamics. You have to, the Lagrangian and the Eulerian picture, which without spin are completely equivalent, and there is a transcendental system of equations to go from one to the other, here they cannot be applied, because as you are showing with this pseudo gauge ambiguity, local equilibration and conservation laws kind of diverge. I mean, I think this is the lesson of all these things. And if you, by default, call hydrodynamics conservation laws, there are some ambiguities that you cannot resolve. But this is the approach. If you think about entropy maximization or free energy minimization locally, you can overcome these things.
Yeah.
Giorgio, but how can you define anything which is not conservation? Only the conserved quantities, they actually are hydrodynamics in the sense that they do behave on long time scales and the distance scales like hydrodynamics. If there is anything else in Lagrangian formulation that is unobservable, it's meaningless.
No, it's not unobservable. It is. Spin and angular momentum can be distinguished experimentally. They have been. I mean, you measure lambda polarization.
Not for a chunk of matter. Not for a chunk of matter.
Yeah, what you can do is define a free energy and have a field of Lagrange multipliers and try to construct an equation of motion for Lagrange multipliers in such a way that the free energy is as close to the local minimum as possible.
You could create anything you want, but spin and angular momentum and orbital angular momentum are not conserved separately. That's it.
No,
how can you separate
that's exactly the point. They're not conserved, but they're observable separately. The Einstein
they are unambiguous. They're not observable because they're not defined separately. They are ambiguous.
I think this is indeed related to what we call hydrodynamics. I think the conventional notion of hydrodynamics is based on just the conservation laws of a specific choice of conserved current. And any further details are just treated as the extra structure, microscopic structure of hydrodynamics. But
I think
it may be possible to develop some sort of extension of hydrodynamics, including such description. But
I think that the entropy current equals 0. I mean, the entropy current equals to 0 is a description of hydrodynamics too. You are very close. You are as close to local equilibrium as you can possibly be. That's a description of hydrodynamics. And entropy certainly distinguishes between spin and angular momentum, even if they're only conserved totally. It's part of the equation of state. There is a spin polarization.
I think
spin susceptibility.
Maybe you are asking about the modification of this first law of thermodynamics, where spin is here. So in fact, this is an important point that I actually regret I skipped. So by doing this, by exploiting this relocation ambiguity of spin current while preserving the conservation, we can make the first law of thermodynamics conventional too, without any spin contribution. So this is another important observation we made, that we can make thermodynamics look as if there was no spin degrees of freedom in the thermodynamic relation. So I know that this is very non-trivial, and our analysis is complicated, but it is possible to remove spin degrees of freedom order by order by exploiting this relocation symmetry in first law of thermodynamics.
There was another question from Masood. Let's give him a chance to ask his question, and then you could continue still if needed.
I wanted to ask a very naive question. When you're saying that you are removing the spin degrees of freedom, is there a price for that? For example, are you introducing new transport coefficients, new equations, or things like that?
Yes, that is a good question. So that's precisely this non-dissipative second order transport coefficient. So by doing pseudo gauge transformation to remove this spin part, as a result, we get the shift of this second order transport coefficient involving some of the vorticity. So in this map between two descriptions, the second order transport coefficients are shifted by definite fashion. So if there was no second order transport coefficient in the spin hydrodynamic description, we will have a non-zero second order transport coefficient in the conventional description. Does that answer your question?
Yes, thank you.
Okay, I think we might still be continuing this. Before we continue unofficially, let me first thank Ho-Ung for a nice presentation.